Hi there. This video will give you a brief introduction on how to use XFOIL. So first, you need to download XFOIL. Okay, here you have the link. Also, in the video description, I will give you a link. And depending on your operating system, you will need to download one version. Also, you can download the source code. Assuming that you are all using Windows, you should click here and download the application. It's a very small program. Okay, so you have Mac. You can download here, click there, here actually, and I don't know if it would work with the latest version. Also, I don't know if it works with Apple Silicon processor, so it's up to you to test that one. But assuming that everybody's using Windows, click there and you will download the software. So when you download the library, you can put that whatever you want. So here I put it in the clean one, I put it in the desktop. So you have this zip file and then you extract everything and you get this. Okay, very small program. Okay, so we're going to focus in XFOIL in this one. Then here you have the source code. For those a little bit more curious, you can read the source code there. So I will go here and will open this folder that I have in my desktop. It's that original installation, but also have some additional files. Okay, so in the video description also you will have the link to download this one. These are additional Airfoils that you can load in XFOIL and some sample output files, okay, from our studies. Okay, so to launch XFOIL, by the way, the source code you have here. So here I extracted and see that this is just this. You want to read the implementation. There is a very interesting file, this one, that is kind of a documentation that you have there. So if you are curious, you can read it. Okay, it's a pure text file, and open it and read it. So to launch XFOIL, okay, click there and you have this screen. Okay, there is no graphical user interface, and actually we don't need it, so don't complain about that. So one thing that you get here, I don't recommend you to maximize everything like this. Just leave it like that, so make it a little bit larger. So always remember that we have a command line interface, so you have the prompt here that is waiting for you to give an input. So to get instructions or help, just question mark, okay, enter, and you have that. So see that here we have a basic, the help, all the commands that we can find. So something just to clarify here, for instance, when you see here this open with a dot, means that there is a submenu. Okay, so you can enter to another menu. Okay, you type open and you enter to, and you will have some options. Okay, in this case, see that you don't have any options. This one will take options, and so on. Also, when you see an F, means that it will generate, it needs a file or will output a file. Okay, a text file, an input file. Okay, then I is integer, it will take an integer. R is a real number, and S is a string. Okay, it's a text. Okay, so those are the symbols. So first we need to read an Airfoil. Okay, so we can read it from an external file or using a Airfoil generator that comes with XFOIL. I will show you the Airfoil generator that comes with XFOIL. So this is the command naka, and then you just type naka. By the way, it's case insensitive. It doesn't matter if you put in capital or small, so it will understand the same. Naka, and then see that it can generate naka 4 digits or 5 digits. It's up to you. So I would generate a 4-digit 2412. Okay, and that's all. So see that it's giving you some information. Okay, it's telling you that generate this one, this basic geometry information. And see that it's still wearing this menu of XFOIL, the main menu. So if I type question mark there, again we get a help. And now that we have an Airfoil in memory, and remember that we're using a panel method that we can control that paneling. There is another option here called PPAR. Okay, so see the show change paneling. So I type PPAR. I don't need to put the dot. The point means that there is a submenu. And see that we enter in PPAR, it will open this graphical window. Okay, leave it there. Okay, you cannot close it as well, so leave it there. It doesn't do any damage. See that it's giving you some basic information, and see that these are the panels. So now we're going to add the sources there, and then compute the circulation and so on. Okay, so here also again, you question mark, you're going to get the actions. Okay, so see here that you can control, for instance, the stretching, bunching parameter, all that stuff, no, how you are clustering the panels. So I'm not going into details. You can play with those options there. So the only one that I'm going to play here is with this one, number of panels. So here you can change it. You type n, and it's going to ask you, see that it's an integer. Okay, it's not a real integer. So how many panels do you want? So you can put 100, 2000, whatever. Usually in the panel method, we don't need to put thousands of panels. So I would say that probably no more than 300 panels. Okay, so in this case 160. Usually XFOIL, what it proposes as default values are okay, but if you want to change it, it's up to you. But don't put more than 300. Okay, so I will change it here. I will put 120 panels. See that I press enter again, and now see that has been updated, 120. So I'm happy with this. Okay, remember we're still in this PPAR menu. So if you want to go back to the main menu XFOIL, you need to press enter, and see that always read the prompt. So see that here we're in the main menu. Okay, so see that at this point we have an Airfoil. We need to run our analysis. So there are different analysis modes. We're going to focus in this video in this one, OPER, direct operating points. Okay, so if you type there OPER, it's going to enter to another submenu. Okay, subdirectory with more options. So see that you have here OPER I. Okay, question mark, and there you have all the options. Okay, I'm not going to address all options, just the most important, but I think they are self-explanatory. Okay. And always also remember that you have also that small documentation. You can see what is happening there. So what is important that when you are in OPER, you see that you have OPER. By the way, if you want to go back to the main menu, enter, and you are back. Okay, so that is the way how you change the directories. So you are in OPER, see this I that you have there. Always pay attention to what you have there. This I that you have there means that you are working in visit mode. Okay, so see that as you go here, you have options to change. So you have this option, and you can change between in visit and viscous mode. Okay, so always pay attention. But for the moment, I want to run a small analysis at a given angle of attack of this Airfoil. So I will run in visit, and see that I want to change the alpha. So you can choose alpha or a target CL. Okay, so I will say alpha 0 degrees. Alpha, enter, and see that it's waiting for the value. It's a real number, so it can be 2.13, 14, whatever. Okay, so I will put 0, and that's all. Now you go here in the screen and you have the information. Okay, so you have CP distribution over the Airfoil. Okay, this is in visit case. Remember that this one is okay, but if you go to 2030, we'll always predict that it's producing more leaves. So be careful if you want to predict a stall and that stuff. You should change to the viscous correction. Okay, later we're going to do that. But see here that you have the basic information. Also be careful, pay attention to the y-axis. Okay, in this y-axis is the axis is reverse. Okay, sometimes people doesn't pay attention to this one. So here you have your distribution and of CP over the surface. So if you want to run for a different alpha force, and that's all. It's super fast. Okay, so the other option is CL. Okay, CL means that you want to reach a given lift coefficient. In our case, it's in visit, so we use CLI. So let's say that I want to find the angle for which I have 0 lift. So I say here, see that it's asking you in visit lift coefficient 0. And now this is your solution. Okay, so see CL0 is, you have it at something about minus 2.11. Okay, so this is the basic in visit computation. So we are more interested in the viscous one. Okay, adding over this panel solution, we're going to add a correction, a viscous correction. You have more information in the documentation, in the source code, that doc file, but also in the slides. The course slides, you're going to find a little bit more information and references to the original paper. So to change to viscous mode, you have this option, visc. So remember that this is almost self-explanatory. Okay, you see the description and you're going to know what is happening. Okay, so I would change to viscous mode, visc, and see that now it's going to ask me Reynolds number. Okay, so remember that in stern aerodynamics or in aeronautics, don't be afraid of high Reynolds number. Okay, Reynolds numbers here is 1 million, 2 million, 5, 10 millions. Okay, don't be afraid of those Reynolds numbers. So I'm going to run for a Reynolds number of 1 million. Put it there, and that's all. See that also can ask, you can give the MAC number. So you type, and you can give your MAC number. Okay, so you put 0 means that is you are not adding compressibility corrections. You put a value, it's going to add some compressibility correction. It's up to you. Be careful that usually MAC number more than 0.5, 0.5, XFOIL is not going to give you accurate results. Okay, but just because you are reaching now the critical MAC number. So for our proposal for the moment, MAC 0, and that's all. Okay, Reynolds, you type, you have 1 million. Okay, let me show it there, and we can run as we did previously. Okay, so I can say alpha 0 and see that this is the solution. So you see here the dashed line that is in basic solution, and also you have superimposed the viscous solution, the color line. So here you have yellow upper surface, blue bottom surface. Okay, so extradose, intradose, or some people also mainly turbomachinery, suction side, pressure side. Okay, so here you have your distribution. Okay, so now this distribution is with the correction of the boundary layer. So you see here that kind of you see a boundary layer here, and you have your values here. So you have CL, CN, CD, lift to drag ratio, and this is a critical amplification factor for the transition model. Also pay attention that here in the output screen, you get this some information as well, a little bit more information than you have here. So importance is that you get here, so you get the same coefficients, but what is important that CD here also you get the breakdown into viscous, friction, and pressure drag. Okay, so you get this breakdown here. So this is total, and you see the breakdown here. And then you have this information here, very important. This is telling you where you have the transition point in percentage of the airfoil core. Okay, so here is about 65% of the airfoil core. You have the transition from laminar to turbulent, and same here. Okay, so that is information that you have here. So I run at alpha 0. Let's say that I want to run now alpha 8. Okay, you can put everything in a single line or alpha and then 8. Okay, it doesn't matter. See that you run and see what is happening here. You have to be very careful. Okay, so usually it converges fast. Okay, but sometimes might happen this that does not converge and you get this message. Okay, so when it doesn't converge, you need to keep iterating. Okay, it uses an iterating method. Okay, for the viscous viscous correction. Okay, with the boundary layer correction. Okay, it's a method based in the Newton method. Okay, for linearization, that stuff. So here it's not converged. You need to iterate more. So see here is you always look at the windows here. It's telling you that exclamation point. You can iterate, do 10 more iterations. Okay, but sometimes that is a little bit annoying that you have a maximum of 10 iterations. So this value you can change it, the number of iterations, and I always recommend you. Okay, you have this option here, iter, that you can change the iteration limit. So I always recommend you to increase that to something about 100. Okay, it's okay. So see that now I change it, and I will go and run again alpha 8, and see that in 19 iterations, and you have a solution. Okay, so alpha 8. So you have to be careful with that number of iterations. You need to increase it, but if you want to increase it, just exclamation point, and it keeps iterating. So again, you have all your values here. Okay, so now what is interesting that this is an iterative method. Okay, it needs to take an initial and starting solution. Okay, to start iterating, and usually that starting solution corresponds to what you compute in your first analysis. So just to explain that again, so there is an option called Init. Okay, so see here, initialization flag. Okay, you are initializing your boundary layer. So I will initialize that. And if I run alpha, usually we run the first computation alpha 0. See that it's very stable. Okay, and then for instance, if we go to alpha 10, see that it's going to take longer to initialize, and sometimes it might not converge because to run at 10 is using as a starting solution data 0. So it's too much difference. So it's recommended to do everything in small steps. Okay, so Again, if I go here, I do alpha 0, then alpha 2, alpha 4, and so on. So do it small steps because your new simulation will use the previous one. Okay, so for instance, now I go alpha 10. It will take longer, but it's fast. But now if I go alpha minus 8, there are completely different solutions. So it might take longer, might diverge, or might not converge. So be careful. See that in this case, it's taking more. So it's not recommended to have those large differences. Okay. So that's all here. So init, okay, I go alpha 0, and that's all. Okay. Interesting things to mention here that you see this small bump here. This corresponds to the transition point here. Okay, so as we saw in the lectures, that can be controlled also with the transition point. So the other thing that I want to show, that we have seen that we can do single simulations. Okay, so single line, but usually we want to plot the polars. Okay, so for instance, stuff like that. No, you can do this plot. So you need to run many simulations. So you need to save that information. So you have seen probably that you can run manually and then just write down this information, I know, in your notebook or a text file. So, but that is not very efficient. So what we can do things automatically. Okay, so as you go here, you see that you have another option called ASEC and CSEC. Okay, this is a sequence of angle of attack, a sequence of CL number. Okay, so as you run this one, we're going to do everything automatically. So, okay, so let me initialize everything. Okay, I will run alpha 0 to have a good solution there. And now I can go as sequence and I can say, okay, first value of angle. So I will say from 0, last one, 25. And see that increment 1 degree or 0.5. Okay, it's up to you. Usually steps of 1 is fine. And then see that is running everything, and you have here all your values. So see that here probably some cases it was having problems converging. Okay, so if it doesn't converge, it's not going to save the information here in this table. So probably it's difficult to read, but see that in this table, this can be saved in text format, and then you can use any software to plot it. Okay, but see that you have here alpha, CL, CN, CD, a moment coefficient, and this is the transition point top and bottom surface. Okay, so this is how you run. Okay, but for instance, you want to save this file, this information. So at this point, we don't have any information saved. We're running in memory. Okay, so to save information, we need to use something that is called polar accumulation mode. Okay, so polar accumulation mode means that, see that you have the option here, PAC. Whatever you run is being saved in memory, and then you can use it to plot directly here in XFOIL, or you can save it in a text file. Okay, so let's do it. So I type PACC. By the way, before entering into polar accumulation mode, you have to be sure that you have the right Reynolds number and Mach number, because you cannot change that information anymore inside polar accumulation mode. So in this case, I'm happy with my Reynolds and my Mach number, so I will enter. I'm in viscous mode, and see when you enter polar accumulation mode, it's going to ask you if you want to save this information in a file. Okay, so if you want to save it, just give it a name, any name. By the way, don't put spaces in the names, just everything together. So in this case, I will save it test1.dat. So everything that I'm going to do is going to be saved here. And then here you have this dump file. So usually don't put anything there. That is for some restarter, but if you want to save something there, it's up to you. And now everything that we're going to do is going to be saved in this file. And see that there is this A here. When you have this A here, means that you are accumulating everything. So to stress that everything that we're going to do is going to be saved in this file. So see that it's automatically all the files, all your output files will be created in the directory from which you launch XFOIL. So see that you have it here. Okay, so now it's an empty file. Okay, but as you keep running, you're going to add information there. Okay, so let's do the same. So for instance, if I go alpha 0, so see that it's giving me a problem. Why? Because I'm using a previous solution. It was the solution 25 degrees. It wasn't a good one. So exclamation point. It still is not converging. So see that it's not a good idea to start from very different solutions. So also be careful when doing this. Init, you initialize, and now alpha 0, you have a converged solution. But if I open here, see that now you have that solution here. So everything that you are doing, okay, is being saved here. Okay, so you save it there. So now if I run alpha 2, you run for 2, so you open here, you have it there, and you go alpha minus 2 will be the same. You have it there. So be careful. You see that I went from 2 to minus 2. It's not a good idea. It's always a good idea to do it in a progressive way. Alpha minus 4, alpha minus 6. And if I go now alpha 1, maybe we'll have problems. I don't know. So see, it showed me some stuff there. But see that everything that you do, you keep here, and then you have this file. You can plot it using your favorite plotting source. Software can be Python, MATLAB, NuPlot, or Excel. Okay, it's not a problem. It's up to you. And you have your information there. So this is it. So just to show you some other options about polar accumulation mode. So always go here and see that you have this plist. It's going to show you the polars that you have stored. PDELs you want to store a specific one. PSORT just to sort that polar. So see that we run this one, it's not in order. So we can sort this one in decreasing from smaller to larger alpha or CL and so on. Okay, so if I type plist, see that you have polar 1, you can have multiple polars. So to save another polar, you need to go out of polar accumulation mode and then open a new one. Okay, to go out, just type PACC. So remember that enable, disable. So you have it PACC. Okay, I think I need to go out, but that will enable this. Okay, here toggle. Okay, you can toggle enable, disable. So for instance, let me use PSOR. Choose the number. Okay, in this case we have one polar. You can have 2, 3. So I want to sort polar 1, and then if I type plist, see that now everything in order. It doesn't order this one, so you need to override it. But okay, so again, let's see more options. So for instance, you have this option pwrite. I think we have it here. Okay, see that you can write the store polar. So you can type pwrite. So remember that when we enable the polar accumulation mode, we also say save it here, but you can say do not save it in the file. You can save that file afterward. Okay, not necessarily you need to enable that. So now you go this, and then I will call it okay, the same file. Okay, it will overwrite, yes. And now as you go here, see that now you have the file in the right order. Okay, so easy peasy. So the other thing that I want to show you that also you can do the sequence of alpha or CL, whatever. So let me switch off polar accumulation mode. Okay, PACC, switch off. See that you have the A there. You disable this, and at this point I can change the Reynolds number. So now I will go to 5 million and enter again in polar accumulation mode, and now I'm going to have another polar. See, polar 2 plist, and see that we have 2 polars. We have the previous, whoops, I gave the file save in the file. Okay, my mistake. Plist, and see that you have the previous polar and the second one. And again, you can save order polars. You just need to check. It is going to ask you which polar do you want to erase, save, or whatever. Okay, so let me run the sequence. So remember always init. Okay, and now I go alpha 0. You have a solution alpha 0, and I can go alpha sequence. Remember, alpha sequence is you go from -6. It's going to start from -6 using what you have in 0. So maybe it's not a good idea. Let's see what happens. 25 steps of 1. So yeah, it's running okay. But when you are running this sequence and you see that you are having problems in some cases, remember that you can do it manually. Okay, so you will pick up those specific cases that didn't work and then run it manually, small changes from a case that you know that works. Usually alpha 0 works, and then from there you change small angles until you reach that value. Okay, to know the cases that didn't work, you go again plist, And the cases that are not saved here are the cases that didn't work. So in this case, all cases work. Okay, we have no problem. All cases worked. See that I have initialization, my first case, and then from here it went to -6, -5, and probably have here 0 repeated. So you can erase one. So for instance, if you want to erase one value, okay, you can save it in the text file and then manually erase it. There is no problem. But also you have here the option that you can remove points. See here, PPAR. So you can erase a polar, or you can erase a single point. Erase a polar, you erase everything. Now I'm going to erase a single point. It's asking, which polar do you want to modify? I want to modify polar 2. And what alpha do you want to erase? So I want to erase alpha 0. There are 2, but it will erase the first one. Put 0, please, and see that it erases the first one, and then you have the second one, and so on. Okay, so now see that you have this data. You can save this data. We saw that in PPAR, but also we can plot this data, okay, to have something similar to what we have here. Okay, these plots, you can have all these plots there. So help, as usual, you have here pplot, plot store polar. Okay, so pplot, and remember we have 2 polars. Okay, so you go please. So you might have the option to plot a single polar or plot everything, or a group of polars. So if I type pplot and I don't give any option, it will plot everything. So see that it's plotting the 2 cases that I have, okay, 2 different Reynolds number, from 1 million, 5 million. Okay, so here we run just of different negative values. So see that you have it here. So see that you have drag coefficient here, leaf curve here. Okay, sorry, this is leaf drag coefficient. This is the polar leaf curve here in function of alpha. Then here, this is difficult to read. Here, this one corresponds to the moment coefficient. So in this scale, it's not very easy to read, but this is moment coefficient, and this is the transition point. Okay, you have it here. So you can visualize that. Okay, so you can use this to plot your data, but I find that it's better to have your own plots. Okay, so you can save this one, for instance, use Excel or Python Magla. It's up to you. So these are the basic steps. Okay, so I would stop this video. Okay, so basically this is what you need to do for your homework. Okay, so in the next video we'll show you now how to read an external file. So thank you for your attention. See you in the next videos. Bye.